Hello and welcome to part 2 of module 7, lesson 3. Let's dive right on in. So we have found that all triangles are cyclic polygons, and as a reminder, cyclic means that it can fit inside of a circle. But now let's examine the possible cyclic quadrilaterals. So we won't actually be using dynamic geometry software right now. You're welcome to. There is actually one attached inside of our Google Classroom for you to access. But right now I want us to just decide this on our own, okay? You'll have a chance to use that geometry software a little bit later. So we're going to decide which word completes the following statements best, okay? So some, all, or no squares are cyclic. Well, let's think about that. If we have a square, could we write a circle, circumscribe is what we call that, around that square, touching all of the points, okay? And if we think about that, I like trying to disprove this, right? As we face each of these, we should try to disprove them. And if we can't, then we'll have to say, okay, it's probably true. So let's say we have this square, sort of. Okay, is there a point at which we can draw a circle that touches all 4 of these vertices, right? And actually, if we think about it, okay, a square, if we look at the center of a square where the diagonals intersect, like this, okay, we know that this is equal to that, that, and that, right? Which, if those are all radii of a circle, that must mean we can circumscribe a circle around that square. So I'm going to say all squares are cyclic. How about rhombuses? Again, I'm going to try to disprove this statement, okay? So I might have a rhombus that looks like this. Now, if I try to make a circle here from the center, this radius would be much smaller than, say, this radius, right? So I actually cannot, in this rhombus, create or circumscribe a circle. It is not cyclic. But think about it. Isn't the one prior a square? Isn't that also a rhombus? Well, it is. So, in fact, actually, some rhombuses are cyclic. Now, how about trapezoids? Let's picture a trapezoid. One pair of parallel sides, the other are not, right? So it could be something like this. Okay. You know, I'd have to say that that is not cyclic, right? This radius is different from that radius. Even, what about if we do it down here? We're closer. That radius might be closer to that radius. You know, that just might actually work. One thing you could do as well to check this is actually use a compass. Draw yourself a trapezoid like this and use a compass and see if you can find a point at which all those points are the same distance from one of the other points. So like down here somewhere. So I'm going to say this one is. But can I think of a trapezoid that could disprove that? Well, think about trapezoids, only one pair of sides is parallel. So maybe I have parallel sides like this, but then I have those sides that look like that. Is there a circle that can be circumscribed on that? Well, after some research on my end, there is actually not a circle that can be circumscribed about those. So, in fact, some trapezoids are cyclic. How about rectangles? Well, think about a rectangle, okay, and you could have varying side lengths as well. But again, the diagonals are something that matter. This point is equidistant from all the other points. So you might have a circle that has a bigger arc on this side and a smaller on those short sides, but it actually, if I was drawing beautiful circles with a compass, they would all intersect, and actually you cannot find a rectangle that is not cyclic. So all rectangles are cyclic. How about parallelograms? Well, we know that a rectangle and a square are parallelograms, right? So those ones can be cyclic, but how about something that's not a square or a rectangle? So what if we have something kind of like our rhombus case, like that? Well, if we're looking at our center, that is not going to be equal to this distance here. So actually, some parallelograms are cyclic, okay? So some generic quadrilaterals are cyclic, and since you can select any 4 points on a circle as the vertices of a quadrilateral, right? So let's say they're just saying here, we start with a circle and we say point 1, point 2, point 3, point 4. That's going to be a rectangle that we chose from 4 random points on our circle, okay? So some are just true by the nature of that. So now you're going to get a chance to use that geometry software that I've linked in your Google Classroom and experiment with cyclic quadrilaterals that are not parallelograms or trapezoids and focus on the measure of the angles and then make a conjecture about the measures of those angles of any cyclic quadrilateral and prove your conjecture using what you know about inscribed angles. So I want you to go ahead and play with that software a little bit and then see if you can come up with a conjecture about all of the angles of a cyclic quadrilateral. Okay, hopefully you were successful in that. My conjecture after doing some of that is that I think every quadrilateral adds up to 360 degrees. The angles do. Now let's think about why. So if I'm going to use a different color here as well. So we have this angle, which is considered an inscribed angle, not a central angle, but we know that that is going to be half the degree measure of this, okay? Now I've got this angle that's half the degree measure of that. Well, total, those two degree measures add up to 360, right? Because it's a full circle. But because it's half, those two equal 180 degrees, okay? Now let's look at the other two angles, this angle and this angle. Well, I see that they're inscribed again, meaning they'll be half the arc measures. So it's half of that and half of this, because we're looking at the opposite arcs, really. So those again make up the full circle, which is 360 degrees. So when we divide it by 2, guess what? 180 degrees. So that means that our blue angles plus our green angles, well, that gives us 360 degrees for the interior angles of a quadrilateral. All right, now that we have that, let's go ahead and jump on to part 3. Okay, and here's another diagram that you could use to kind of do a flowchart proof or a paragraph proof explaining what I just did on the last page. Okay, so let's look at part 3. In task 5.8, we worked on Colton's notes and we decided it was possible to locate a point that's equidistant from all 3 sides of a triangle, and therefore a circle can be inscribed inside of every triangle. So there's a difference between inscribing a circle and circumscribing a circle, right? Circumscribing is using the vertices to surround a circle, whereas inscribing, you're making a circle within the circle, or within this triangle, okay? Something like that. So what your task now is to use a compass and a straight edge to construct the circle that can be inscribed in each of the following triangles. You'll need to construct angle bisectors to do so. And then once you've located the center of the circle, determine how, or tell me how you determine, or tell below, how you determine where the points of tangency between the circle and the sides of the triangle are located. So the points of tangency are where it just barely touches. But how do you decide those points, right? That's your question. So go ahead and practice that and see if you can figure out where those points of tangency are. Okay, hopefully you have done that and inscribed beautiful circles inside of each of these triangles by creating the angle bisectors. Remember, you use a compass to create that little arc. based off of these 2 points, you use the same compass measure so you don't change it, and create those 2 hashes. Boom, there is your angle bisector, and you do that for all 3 sides, or all 3 angles, excuse me, and you will get a point at which they intersect. That's probably a little too big of a point. Hopefully yours is smaller. So now we need to determine, okay, how do we figure out how to actually inscribe this circle? So what you need to do then is you'll have to drop a perpendicular line here, okay? One pretty handy way to do that is to use your compass and see where the absolute longest it is before it touches, and that's going to be your tangent line. That's going to be perpendicular. Or you can also use your compass and create a hash like this from this center point here, and then create the perpendicular bisector of that segment, and that will be a perpendicular line that intersects this point, okay? So that's one thing you can do as well. But in so doing, either way that you choose, this is now your radius of your circle. So use your compass at that radius, and it should just barely touch each side. It will be just tangent to each side of your triangle. Okay, and you can do that with all 3 of those triangles. So you'll want to do that as well. So now, angles formed by lines that are tangent to a circle are called circumscribed angles, right? Use the dynamic geometric software attached that you've used once already to experiment with the measures of circumscribed angles relative to the arcs they intercept, okay? So, looking at arc AC and deciding, okay, how does that relate to this angle right here, okay? So that's what you're going to kind of be looking at. See if you can figure out if there's any relation between the arc and the angle CBA. So go ahead and give that a try. Well, hopefully you have been successful in part of that as you've been meandering through that software. We are going to go ahead and prove this in our lecture. So please join me in our lecture today, and we will go ahead and prove this so that we can look at what we've actually seen and go from there. We'll also cover number 8 in today's lecture as well.